For this discussion, we're going to start our journey into Maxwell's equations, starting with Gauss's law. So, in particular, in this video, we'll talk about the integral form of Gauss's law. So our Maxwell's equations journey has begun. I want you to be able to do two things. I want you to be able to use it to derive the E field for an expression, but also be able to explain it in plain English. So let's start with the plain English version of it. Or actually, I lied. Let's start with the fancy math version and then describe it in plain English. So in the fancy math version is that d dot ds closed integral, which is from our definition of electric flux density that we talked about before, is equal to epsilon E dot ds, is going to be equal to the Q enclosed. Or if it ends up, you're describing the charge as a volume charge density, it's going to be equal to rho v dv. So this is ultimately Gauss's law in integral form. Now let's move on to plain English. Now the plain English version we actually talked about before. So let's start with the point charge example. The point charge has all of these E field arrows radiating outwards. And remember previously I said that the total number of arrows is going to be equal to Q. That's effectively what Gauss's law is saying. What Gauss's law is saying is if I draw a closed surface, any kind of closed surface, that's what this circle in here means, and add up all arrows of a closed surface equals Q enclosed. So in other words, the total electric flux coming out of a closed surface so closed being key, so they actually capture all the arrows that would emanate from the charge in question. That's going to be equal to the total charge inside. And so that's what the left half of this equation. So I'd say the left 3/4 of this equation is I take the electric flux density multiplied by the area. That is going to give me the total amount. Arrow density times area is going to be equal to arrows, right? So add up all the arrows, that's going to be equal to the charge inside. And since in many cases we're going to, instead of just giving you a point charge, we're going to describe the charge in terms of a charge density. So in that case, you would use prior skills to find the total amount of charge, which is integrating over the volume of that charge, right? The next thing is how we would use that to find the electric field. So use Gaussian's law in integral form to find an electric field. And to do that, let's just break it up into a few key steps. First step is just our stop and think step. So find the coordinate system and also, since you're doing a surface integral, define your ds, right? And the main key is you want to use symmetry. Now, what do I mean by symmetry? Let's just start by, if we're going to use this to find an expression for the specific purpose of finding an expression of the E field, what we want is, I'm going to define symmetry as that the field direction for that entire closed surface can be described by one of the letters of x, y, z, rho, phi, or theta. Okay, so what you want to do is you want to say that you want to find a particular direction. You want to set your coordinate system such that one of these letters can describe the E field. So you can already see right now that Gauss's law in integral form can only be used to solve problems in highly symmetric, highly simple situations where all of your field, again, using your intuition, can be described by one of these basis vectors. Once you have that, the next step is to write out your expression for the electric flux density, which is going to be equal to, I'll just leave this part blank since we don't know what it is, but whatever this letter is, so if it's all in the rho direction or the r direction, actually I forgot to add the letter r on here, is also a valid choice. That would be r there. But basically, we chose a coordinate system such that it could be described using one basis vector. So write that expression, use that to write out your expression for electric flux density. And again, this rectangle can be either r or rho or xyz, one of these basis vectors. So once you have that, evaluate the double integral of d dot ds, where ds is something that you found over here. Now, one of the important things to recognize is that for this approach to work, you need your expression here to not vary by the elements of ds. So to give a very specific example, in order for this to work out, if this is, say, a function of rho, that means your ds will be, the other two numbers. So that would be rho d phi and dz. In order for Gauss's law in integral form to actually work, you need e rho to not be a function of phi and z, so you can pull it out of the integral. So you want to be able to write that, you want to be able to do this. You want to be able to pull the E field out so that you're just integrating over d phi dz, and there's no E in this integral. If you can't satisfy that, then Gauss's law in integral form probably won't be able to solve the problem that you're trying to apply it to. So make special note that this is what I mean by symmetry, is that you can describe the field using one of these letters, and furthermore, your expression for E field must be such that this E term can just be pulled out and is independent of phi and z. If that is not the case, then you need to use a different approach. And in the past, there have been many people, since the integral form is easier to understand intuitively compared to stuff we'll talk about later, there's a very strong temptation to apply this to situations where it won't work. And so I think it's really important to really know be able to determine when this integral form is the right path. So again, make sure you can describe it by one of these letters. And when you're setting up this integral, the left-hand side of this equation, make sure that you can pull all the E field out and that it's not independent of your remaining two length vectors, or the vectors that form ds. Once you have that, the next step is to gather all the information for the right half of this equation. So if you're given the total charge, then great, then you're done with that. But if you need to, you may need to go through some extra work to find Q enclosed by doing a volume integral or some other math to find what total charge is inside this surface. And then step 4 is you set up Gauss's law, so you write out epsilon E ds is going to be equal to Q, and then pull out this electric field expression. So again, this works because you can pull that E out, and so solve for E of something is going to be equal to, do this integral, pull everything out, and move it to the other side. So then you can use that to get your expression of your E field. So this will be a little bit more easier to understand after you work through a few examples. But again, just as a quick recap, Gauss's law in integral form in plain English is saying if I draw a closed surface, meaning I capture all the arrows that might be coming out of all the charges inside, if I add up all the arrows, so and that's the equivalent of saying arrow density times area, right? Will give me the total number of arrows. The total number of arrows will be equal to the charge inside. Or to use the water analogy, the total amount of water flowing out of a closed surface will be equal to the the strength of your water source inside, right? Or water sink. So if you have a negative value, if you find out you have a bunch of arrows going in net, then that tells you how much of an arrow sink you have inside, right? Or continuing Star Wars analogies, if you add up all the amount of force that you feel surrounding in a closed surface, that tells you the amount of Jedi power or Sith power that's sitting inside that closed surface. That is Gauss's law in English. But to use it to solve problems, you can use this to solve for electric fields in highly symmetric situations by first finding the coordinate system, finding your ds, and choosing that so that you can apply symmetry. So symmetry has two criteria. One is that your field can be described by one basis vector. So x, y, z, rho, phi, theta, r. And in that case, your ds will be the other two letters in your coordinate system. And the second criteria is that your expression for the electric field has to be independent of the ds terms. So in this example, if you decide that your E is in the rho direction, it has to be, you have to be able to write it in a way such that it's independent of phi and z. The main purpose of that is ultimately in step 4, you want to be able to pull E out of the integral and shove everything to the other side to come up with your expression for the E field. Once you have that, you then come up with how much charge is enclosed. Set the two to be equal to each other, as I mentioned before, pull the E out of the integral, shove everything to the other side, and this will give you a Gauss's law of integral form approach to calculating the E field, which can be easier than Coulomb's law, but as I mentioned before, only works in highly symmetric situations.